Assalamu alaikum students. Article for today is magnetic field due to a current carrying solenoid. This is the other next application for Ampere's law in case of solenoid. What is basically a solenoid? Consider solenoid just like a spring, right? What is a spring? If I'm going to describe you, there is basically a wire which has been given a number of turns and turns and turns and turns so on, and we have turned that particular straight wire into a solenoid or in a curved configuration. This is basically known as the solenoid configuration. If I draw that solenoid, I can draw it this. Like this is the configuration for the a solenoid, right? From one particular point current is going to enter, and from the other point it is going to be definitely coming out. We have read in our previous articles or in the previous classes that the field of the solenoid is basically a straight inside the conductor, inside the solenoid, and it is, sorry, I've drawn it in the wrong way. Okay, so this kind of stuff we observed and we have read in the previous classes that inside the solenoid the field is parallel and strong, and outside the solenoid the field is weak. Outside the solenoid we are definitely seeing that this would be the circular path and this would be the circular path we are going to observe. Outside that particular solenoid the field is curved, but inside the solenoid the field is parallel, number one, number two, uniform, and number three, strong, right? So the field which we are going to consider in the case of solenoids would be definitely inside the solenoid, because the field is uniform in this situation, which is the basic requirement for drawing the Ampere's loop. Number two, the field is parallel, field lines are parallel to each other, that means they're equidistant. And the third one is or the field lines which we have drawn, they are all in the same direction. And last but not the least, the field is very strong inside the solenoid, but outside the solenoid the field is weak. Why it is weak? Because we are definitely moving away from the conductor, and as we move away from the conductor the field is going to be weak. Inside the solenoid the field is going to be very strong, right? So for this particular configuration we have seen that inside the solenoid the field is going to be straight. Now you must be thinking that how it is possible that if for a straight wire the field lines are going to be the circular ones, and in this particular case for the solenoid the field is going to be straight. How it is possible? So to understand that phenomena we are going to know the certain factors. Number one, what is basically number of turns? ठीक है, number of turns basically हमारे पास क्या चीज़ होता है? So to know that factor we know that, consider there is a length element which is equal to this is equal to suppose 1 meter. ठीक? In this condition I'm going to draw the field the number of turns. Like in this condition there are probably 1 2 3 4 or 5, you can say, number of turns are there. Next I'm going to do for the same length, that is again of 1 meter. Again if I want to draw the number of turns I can draw it also like this. And in this case I observe there are only two number of turns are there, or you can say three if I draw it like this. So there are three number of turns, but there can be another case in which for the same length, that is 1 meter, the number of turns could be like this. right? So in this condition, these are not drawn in the appropriate manner. I don't have a good diagram stuff, so avoid that thing. There are more number of turns in this situation. So this phenomena which we are going to discuss is basically known as a number of turns per unit length. So how can I write it? I can write it like this, that number of turns per unit length is equal to n. And what is basically n? What n is it is basically known as the um, turns per unit length, number of turns per unit length, right? Or simply the turn density, right? So this factor, that is small n, it is equal to number of turns per unit length. And if there are more number of turns, definitely field would be definitely more strong. And if there are less number of turns, the field would definitely be going to weak. And how I'm saying that b is in this case, that how if I, by increasing the number of turns, b is increasing, and so on, I will definitely explain that thing in the last formula which we are going to derive. Now we know that for a straight current carrying wire, the field line we draw is in the circular path. For if I want, like, suppose this is the if the current is flowing through, this is basically I've drawn a turn, right? As you know that the turn is like this, so this is basically a circular path, right? So I have drawn that circular path in this situation. If this circular path, like if I'm drawing the direction of current as well, current is flowing like in this direction. If I want to draw that thing on this particular circuit, sorry, in this particular loop, I will draw it like this, right? This is the direction of current would be there. Now if the direction of current is like this, and I want to apply right hand rule over here, and if I grasp this particular wire at this particular point into in my right hand, and the current thumb is indicating in the direction of current in the upward direction, and the curl of the finger would definitely be indicating that the direction of magnetic field would be anti-clockwise. So if I want to draw that thing, it would be like this, right? So this would be like towards me, out of the screen. How would I draw that? I'm writing it like this, right? This basically inside, I'm talking about inside the loop. So inside the loop, the value at this particular point, I'm talking about at this particular point in this region, the value of b would definitely be out of the page or out of the screen or towards you, right? Now if I want to determine, like at this particular point, if I want to determine the direction of magnetic field, I would definitely draw the direction of current. So at this point the direction of current would be like this, and I want to draw now the magnetic field by again using the right hand rule. The magnetic field would be like this, right? And in this condition, again if I observe, and again if you use your right hand for this purpose, the magnitude or sorry, the direction of magnetic field inside the loop, like at this particular point, again in this region, the value of magnetic field would definitely be out, that is towards you, out of the page or out of the screen. Now at the third point, in this region, the direction of current is in the downside direction. If I use again the right hand rule for the same purpose, and observe the magnetic field into the region, it would can be drawn like this magnetic field, and in the central region, like in this particular, at this particular point, the direction of magnetic field would definitely be out of the page or out of the screen. And last but not the least, at the fourth point, this point. If I want to determine the magnetic field, I would definitely use again right hand rule. And if I see inside the loop, like at this particular point in this region, the direction of magnetic field would again be out of the screen. Now at every point you choose, like at any point, suppose I've chosen this point, or I have chosen this point, this point, this, at any point I have chosen, the definitely the magnetic field would be drawn, that would be circular. And for inside this particular loop, the direction of magnetic field would be towards you or out of the screen. And if I want to draw this clearly, more clearly in a figure, so I would write it like this, draw it like this. At this particular point I would draw a dot. Now what is this basically, dot and cross? If you have seen a dot inside a circle, that means the field lines is out of the screen, right? And if you see a cross, if you see this cross inside the circle, then in this particular case this shows that the field line is into the page or into the screen or away from you, right? So in this particular case, what we have observed, that for every point the field lines are out of the page, right? So I'm using this dot to show that for at every point the field lines are out of the page. Now what you are going to observe, all the field lines, they are coming towards you, right? And for this particular turn, like for this particular turn, if I draw it like this, all the field lines, they are coming, they are moving in this condition, that is away from you, right? I've drawn it in this way, away from you. I have simply changed the direction, like from the surface level I have drawn, I've tilted that particular turn. So all the field lines are having direction in the right side. Now we know, we have discussed that thing, that the field lines are going to definitely be curved, they definitely be curved as they move away from the conductor. So as the time comes that they are going to get a curve, we have drawn another set of loop. Then again for this particular loop, what is going to happen, all the field lines would be again the same condition, coming out, right? And the moment they are at the length, like suppose after 1 meter, suppose after 1 millimeter, they are going to change their direction from straight line to curved. So after 1 millimeter we are again going to draw another loop, right? So again their direction would not get curved, and for this particular loop all the field lines would come out, right? So that's how for all of the curves, for all of the turns which we are going to draw, the field lines would definitely be in the forward direction, that is out, right? And that's how we say that for any uh, solenoid for any solenoid, the field lines are going to be straight inside the conductor, but they are going to be curved outside. I hope you are getting my point now, that how you say that all the field lines, they are going to be straight inside the conductor and curved outside the conductor. Okay, now the same configuration which we I'm going to draw is choosing the same solenoid, right? And the current flowing through this particular solenoid, which we are going to, is like this, right? So in this particular state, Definitely there would be number of field lines. I usually draw three of them just to show you that they are going to be curved outside, right? This is definitely going to be curved outside, right? Like this. So in this state, we have seen that all of the field lines which we have drawn in this particular case using the right hand rule, if I want to draw that thing, um, this is the case. I have drawn the direction wrong. Using the right hand rule, so using the right hand rule, if I use this kind of direction, then direction of field lines would be like this, right? And this is going to be opposite to your book, so I'm going to draw it again according to your book stuff, right? um, so according to, okay, so I've drawn it according to your book, and in this situation, according to right hand rule, the curl in the direction, curl of the fingers is in the direction of current, and then the thumb indicates the direction of the north pole. So definitely field lines are emerging out of the north pole, like this is the north pole and this would be the south one. Why? Because field lines are emerging from north and entering into the south one. Now to describe B at any point inside the magnetic field. Suppose we have chosen this point P. This is the point P at which I want to determine the B, that is the magnetic induction. So for this purpose, what we are going to do, we would definitely be going to draw an Amperian loop. Now the question arises, can we draw a circular loop for this purpose? No, we cannot. Why? The reason behind is circular path provides you the value of B for single configuration. Single configuration means that the value of B in that case was depending upon R, and in that condition R was same throughout the surface, throughout the loop. So R was constant, that means B was uniform. But in this particular case, what we observe that for the particular point P, we are not going to get the same results. B is going to be different at suppose this particular point, and it is going to be definitely different at this particular point, and center it is again different, outside again it is different. So for all these configurations, what we are going to do, we are going to change the geometry of our Amperian loop. What we are going to draw, we would definitely draw this particular Amperian loop in the form of a square, you can say, or a rectangular form. So I'm going to draw this particular geometry, and this is known as the Amperian loop. This is this closed one. B is uniform in this region. How can I say that B is uniform in this region? B is uniform like from for the portion which is known as um, L1, and this is described as L2, this is L3, and this is L4, right? So for all these points, we are going to see that is B constant or B uniform or not. So we observe that for L1, B is obviously same, right? B is constant, that is the value of B is maximum, or you can say B is the strongest in this region. What about the case if we are using L2? For L2, what we are seeing that for L2 and L4, for these two values, for this and this as well, for these two values, we are getting the condition in which B is basically not the strong one, like the value of B is decreasing. And for the portion L3, what is going to happen? There is a very weak field for this particular L3 element. So that means B is not uniform in this condition. Why we have drawn this particular symmetry in the circle, in the square shape? So for this purpose, we are getting, basically, if we are not finding a single configuration, we move towards the two configuration system. What is meant by two configuration system? We are observing two symmetries for magnetic field here. How? For the first symmetry, we are observing that theta between L and B is 0 degree, like for the case inside the solenoid, because inside the solenoid you're observing that L and B are in the same direction. And for the cases of L2 and L4, we are observing that theta is equal to 90 degree, right? How you can see this? You can see that this is the value, or this is the length element, L4, and if I want to draw the angle between um, field line and this particular Amperian loop B and L, the angle is going to be definitely 90 degree. So this is 90 degree, right? And again, for the third configuration, for L3 side, what we are going to observe that for this Amperian path, if I draw the directions as well, this is the direction L1, this is L2, this is L3, and this is L4. So for this loop, if I want to see the direction for the angle for L3 and B, this theta is basically equal to 180 degree, right? Now you must be thinking that why 180 degree, because I've already mentioned that we are going to be discuss two symmetry system. Basically in this case, L3 would definitely be having no magnetic field, because we don't consider the magnetic field outside the solenoid, since inside the solenoid the field is so strong that outside the solenoid the field is very weak, which is generally ignored. So for this particular case, for L3, the field would be equal to 0. So this configuration would ultimately be considered as a two symmetries for B. Now to understand that thing, I'm going to calculate the result for this particular configuration. So for that purpose, what I'm going to do, I would definitely draw sorry, I will definitely calculate the you calculate by using Ampere's law formula, which is basically summation b dot dl this is equal to mu naught I. Take. Now we know that for the whole configuration, what is going to happen for L1. If I want to determine for this particular case, for this L1 side, what is going to happen for L1, we are having an angle of 0 degree between B and L, right? So there is an angle of 0 degree, so I can write for the first side, I can write B dot, sorry, dot would be reduced, I would write L1 cos theta, and the value of this theta would be, okay, so I've used the whole of the equation, and this whole equation would suggest that for the side L1, the as you can see, the angle between L1 and B is equal to 0 degree. So I have mentioned BL1 cos of 0 degree for this side. Now coming towards L2, we have seen that there is an angle of 90 degree between L2 and magnetic field B. So I would write 90 degree for this case. And for the third case, we have L3. Direction of L3 is towards the right side, and the direction of magnetic field is towards the left. So in this particular case, we are going to put the angle 180 degree. And for the fourth side, we again observe that B and L are perpendicular to each other, so we are going to put the angle equal to 90 degree. This whole would be definitely equal to mu naught I. Now I'm going to put the values. For the first case, in which we have put the cos 0 degree, the cos 0 degree gives you the value 1, so we are going to receive for this case BL1. Now for the next one, BL2 cos of 90 degree. Cos of 90 degree is equal to 0, so this whole term would be equal to 0. So I would write 0 over here. For the third case, BL3 cos of 180 degree. BL3 cos of 180 degree, cos 180 degree is equal to -1. But since this L3 side is basically out of the solenoid where the field is very weak, and that weak field is basically negligible, so this whole thing can be replaced by 0, since at the L3 region B is equal to 0, right? It is negligible, so we definitely don't consider it at, and the value of B can be put equals to 0, and ultimately you get the answer. Now for the fourth side, that is for 90 degree, again cos of 90 degree is equal to 0. So for this fourth side, we are going to receive again answer equal to 0, and this is equal to mu naught I, right? So ultimately what we have seen that B L, or generally if I'm writing, so BL simply, or BL1, if whatever you want to write, this basically equal to BL equals to mu naught I, right? Okay, so what we lastly what we derived, BL equals to, or some BL1 equals to mu naught I, right? This I, now I'm definitely going to see that what is the net current which is flowing through this particular solenoid. So for this particular solenoid, we observe, I can write L1 as well, 1 as well, was previously written. So I'm going to see that from the Amperian loop, in this particular Amperian loop, how the current is passing, right? So what would be the value of the net current? So if I'm going to notice the current through a single turn, that current would definitely be equal to I, right? If there are two turns, then the value of current would be 2I. If there are three currents, the value of current would be 3I. If there are four number of turns, then definitely the value of I would be 4I and 5I and 6I, by increasing the number of turns. So if there are n number of turns, so the total or the net current through that loop, I net, would in this case be equal to I into n number of turns, right? So this if I'm going to put this value of net current in the in our equation, above equation, it would become BL1 equals to mu naught n I, right? Now if I'm going to put the value of this capital N, previously we have used the formula that which was known as turns density. It was N equals to number of turns per unit length. If I want to get the value of N from this situation, then it would be NL, and we know that only L1 is the side through which we are going to receive the magnetic, because we are going to definitely determine B at that B on L1, so we are going to consider this length L1. If I put the value in the formula, what I'm going to get, mu naught n L1 into I, and this L1 would be cancelled on both sides, so B would be equal to mu naught n I. This is the final value which we are going to get for our solenoid configuration. This is the answer which we are going to get. So that was the article for today. Thank you so much. Allah Hafiz.